Welcome to Earthly Teachings, where learning is clear and powerful. I'm your instructor, and today we're working on Mathematics N6. We'll be tackling a comprehensive summative assessment for Module 4, focusing on solving various types of differential equations. Let's learn together. By the end of this video, you will be able to determine both general and particular solutions for a wide range of first and second order differential equations. You'll gain a deeper understanding of methods like separation of variables, integrating factors, variation of parameters, and the solution of second-order linear homogeneous and non-homogeneous equations. You'll also learn to apply these concepts to practical problems. We'll begin with the first section, where the goal is to find the general solutions to a set of differential equations. Let's start with question 1.1. The question is, determine the general solution of d/dx plus y out 3. This is a first-order linear differential equation. A common method to solve this is using an integrating factor. Remember that the standard form for a first-order linear differential equation is dx plus pico xy equals x. Our equation already fits this form perfectly. Comparing our equation, dx plus y equals 3 to the standard form, we can see that px is 1 and cos is 3. Now, the next step is to find the integrating factor, which we call I. The formula for the integrating factor is I equals e to the power of the integral of p is key with respect to x. This factor will simplify our equation significantly. Plugging in px equal 1, we get I equals e to the power of the integral of 1 dx, which simplifies to just e to the x. The beauty of the integrating factor method is that the left side of the equation, once multiplied by I, becomes a perfect derivative. The general solution is given by I times y equals the integral of I times q x dx. Let's substitute our values. We have e to the x times y equals the integral of e to the x times 3d. The integral of 3e to the x is just 3e to the x. And since it's an indefinite integral, we must add the constant of integration, c. Don't forget this, it's a very common mistake. Finally, we need to solve for y to get our general solution. We can divide the entire equation by e to the x. This gives us y equals 3e to the x divided by e to the x plus c divided by e to the x. The e to the x terms cancel, leaving us with our final general solution, y equals 3 plus c times e to the power of negative x. Now let's move on to the next problem, 1.2. The question asks for the general solution of dx minus y over 2x equals x to the 2 times e to the 2x. This is another first-order linear differential equation, so we'll use the integrating factor method again. First, let's identify px and qx. Px is the coefficient of y, which is 1, 2x, and qix is the entire right-hand side, x to the 2 times e to the 2x. Our next step is to find the integrating factor I by integrating pt. We need to calculate e to the power of the integral of negative 1 over 2x dx. The integral of 1, 2x is negative 1 half times the natural log of x. Using a log property, we can move the negative 1/5 into the exponent of x. Then since e and ln are inverse functions, they cancel out, leaving us with I equals x to the negative 1/2 of or 1 over the square root of x. Now we have our integrating factor. Let's find the general solution using our formula. The solution is y times I equals the integral of I times qx dx. Substituting our values, we get a y times x to the negative 1/2 equals the integral of x to the negative half times x to the 3/2 times e to the 2x dx. Let's simplify the term inside the integral. Using the rules of exponents, we add the powers of x. Negative 1/2 plus 3/2 equals 1. So the integral simplifies to the integral of x times e to the 2x dx. This is a standard integral that can be solved using integration by parts, but for the sake of time, we'll state the result directly and you can confirm it on your own. So our equation is y times x to the negative 1/2 equals the result of that integral plus our constant of integration, c. To isolate, we will multiply the entire equation by x to the 1/2, or the square root of x. Multiplying through by x to the 1/2 We get y equals 1 times x to the 2 times e to the 2x minus 1/4 times x to the 1/8 times e to the 2x plus c times x to the 1/8. And that is our final general solution for this problem. Let's continue with problem 1.3. This one looks a bit more complicated, so let's break it down. The equation is x di dx plus y times the quantity 1 plus x cot x equals x cos x. It's a first-order linear differential equation, but it's not yet in the standard form di dx plus pxy equals qx. The standard form is di dx d plus pxy equals qx. Notice the dA dx term has a coefficient of 1. To get it into the standard form, our first step is to divide every term in the equation by x. Dividing by x, we get di by size dx plus y times 1 plus x cot x over x equals x equals x over x. This simplifies to di slash dx plus y times 1x plus cot x equals cos x. This is now in standard form. From this, we can identify p as 1 at plus cot x and qx as cos x. Next, we find the integrating factor I. I equals e to the power of the integral of p px d dx, which is e to the power of the integral of 1x plus cot x dx. We can split the integral. The integral of 1 is ln x, and the integral of cot x is ln of the absolute value of sin x. Using log properties, the sum of logs is the log of the product. So, our integral is ln of x sin x. Therefore, the integrating factor I is e to the power of ln of x sin x, which simplifies to just x sin x. With the integrating factor in hand, we can now find the general solution. The solution is I times y equals the integral of I times qx dx. Substituting our parts, we get x sin x times y equals the integral of x sin x times cos x dx. The integral on the right, the integral of x sin x cos x, is a bit tricky. We can use the trigonometric identity that 2 sin x cos x equals sin 2x. Rearranging this, sin x cos x is 1/2 sin di. This substitution simplifies the integral. Our integral becomes the integral of x times y half sin 2x dx. We can pull the 1/2 out. This integral is now in a form that requires integration by parts. Let's perform the integration by parts separately. We'll let u equal x and dv equals sin 2x dx. If u equals x, then do is dx. If dv equals sin 2x dx, then integrating gives us v equals -1/5 d cos 2x. Applying the integration by parts formula, u times v minus the integral of v du, we get -1/2 pp cos 2e plus the integral of 1/2 pp cos 2ex dx. Integrating cos 2x gives 1/2 sin 2x. So the result of our integration by parts is -1/2 cos 2x plus 1/4 sin 2x. Since we had a 1/2 factor in front of the original integral, our full integral result is -1/4 cos 2x plus 1/8 sin 2x. Let's put it all together to find y. We have x sin x times y equals -1/4 cos 2x plus 1/8 sin 2x plus c. To solve for y, we divide by x sin x. Distributing the division, we get our final, somewhat complex general solution. Y equals -1/4 cot x times cos 2x over x plus 1/8 cos x plus c over x sin x. A key takeaway here is that sometimes you need to manipulate the equation algebraically before you can solve it. Question 1.4 presents another interesting challenge. The equation is ln x times di dx minus y over x equals the natural log of x squared. Take a moment to look at this. Does it look familiar? It has a term with y, so it's linear, but just like the last one, it's not in standard form. The dl/dx term has a coefficient of ln x, but we need it to be 1, so our first step is to divide everything by ln x. This gives us di dx minus y over x ln x equals ln x. Now it's in standard form, and we can identify px and qx. P is the coefficient of y, which is -1 over x ln x. Qx is the right side, which is ln x. Time to find the integrating factor I. I equals e to the power of the integral of 1 over x in xd. This integral requires a u substitution. Let's let u equal ln x. Then the derivative of u with respect to x is do dx equals 1 dx, which means dx equals x do. Substituting this into our integral, we get the integral of 1 over xu times x do. The x's cancel, leaving the simple integral of 1 over u do. The integral of c in u is a ln in du. Substituting back for u, we get e in e. Now plugging this back into our integrating factor formula, we have I equals e to the power of t ln x at c. Using log properties again, e and ln cancel, leaving us with I equals ln x to the power of -1. This means I is 1 over ln x. This is a very elegant simplifying step. With our integrating factor, we can find the general solution. The solution is y times I equals the integral of I times q to x dx. Substituting our parts, we get we over ln x equals the integral of 1 ln x times ln x dx. Look at that. The ln x terms in the integral cancel each other out. This leaves us with the very simple integral of 1 dx. The integral of 1 dx is just x, so y over ln x equals x plus c. Finally, we solve for y by multiplying both sides by ln x. This gives us our general solution. Y equals x ln x plus c ln x. This problem seemed tricky at first due to the natural logs, but by following the standard method, it's simplified beautifully. It's a great example of how differential equations can guide you to a surprising result. Question 1.5 might look a bit different from the ones we've done so far, but it's another linear first-order equation. We need to find the general solution of x squared di x plus 2xe equals secant squared x plus cosine x. Again, our first step is to get the equation into standard form. Di d da x p equals p y equals q. We must divide every term by the coefficient of di dx, which is x squared. This gives us di dx plus 2xy equals secant squared x plus cosine x all over x squared. Now that it's in standard form, we can identify p and q. Px is the coefficient of y, which is 2 by xy. Qx is the entire right-hand side. As we've seen, this is a crucial first step. Next, let's find the integrating factor, I. I equals e to the power of the integral of p dt, which is e to the power of the integral of 2 d dxd. The integral of 2 baus is 2 len I x. Using a log property, we can write this as ln of x squared. Then e and ln cancel, leaving us with I equals x squared. This is a very simple integrating factor. It's a great opportunity to show a memory trick or an alternative way to solve the problem. Let's rewrite the original equation. X squared di dx plus taki. Does this look like the result of the product rule for differentiation? Recall the product rule. The derivative of u times v is u prime v plus uv prime. If we let u be x squared and v be y, their product is x squared y. The derivative of this product is 2x times y plus x squared times di d. This is exactly the left side of our equation. So, we can rewrite the equation as the derivative of x squared y with respect to x equals secant squared x plus cosine x. This is a much simpler form to integrate. This memory trick is very helpful in exams. To solve for y, we integrate both sides. Integrating both sides with respect to x gives us x squared y equals the integral of secant squared x plus cosine x dx. Remember the standard integrals. The integral of secant squared x is tangent x, and the integral of cosine x is sine x. Of course, we add our constant of integration, c. The final step is to solve for y by dividing by x squared. This gives us our general solution. Y equals tangent x plus sine x plus c all over x squared. This alternative method shows the deep connection between differential equations and basic differentiation rules. Our final question in this section, 1.6, is a special type of equation. The equation is secant squared y times di slash dx plus 1 over x times tangent y equals sine c. The question provides a helpful hint. Let t equal tangent b. This is a nonlinear equation, specifically a first-order nonlinear differential equation, which we often can't solve directly with the linear methods we've been using. The presence of secant squared y and tangent y suggests a substitution might work, which is exactly what the hint is for. This is a common exam strategy. Look for substitution opportunities when a problem doesn't fit a standard form. Let's follow the hint and make the substitution. If we let equal tangent we need to find an expression for di/dx in terms of dt dx. We'll use the chain rule for this. The derivative of t with respect to x, dt dx, is equal to the derivative of tangent y with respect to y, times the derivative of y with respect to x. The derivative of tangent y is secant squared y. So we have dt dx equals secant squared y times di dx. Now we have everything we need to substitute back into the original equation. Notice that secant squared y dir dx is exactly what we found to be dt dx, and tangent y is just t. Making these substitutions, our equation becomes dt dx plus 1 over x times t equals sin x. Look at that transformation. We've turned a difficult nonlinear equation into a simple linear first-order differential equation for t. We can now solve this for t using our familiar integrating factor method. P is x and qx is sin x. Let's find the integrating factor for t. The integrating factor I equals e to the integral of 1 by t dx, which is e to the ln x, or just x. The solution for t is t times x equals the integral of x times sin x dx. The integral of x sin x can be found using integration by parts, which gives us negative x cosine x plus sin x. Now we've solved for t, but the original equation was in terms of y. We must substitute back to find y. Remember our substitution, t equals tangent y. So tangent y times x equals negative x cosine x plus sine x plus c. Dividing by x, we get that tangent y equals negative cosine x plus sine x over x plus c over x. The very final step is to solve for y. We take the inverse tangent of the entire expression. So y equals the inverse tangent of negative cosine x plus sine x over x plus c over x. This problem demonstrates the power of substitution to simplify complex differential equations. We have completed the first section. Now we move on to the second section of our assessment, which deals with second-order linear differential equations. The general form of these equations is a double prime plus by prime plus psi equals f of x. The solutions have two parts, the homogeneous solution, y(h), and the particular solution, yp. The general solution, y, is the sum of these two parts. Let's tackle them one by one. Let's begin with the first problem in this section. 2.1. The equation is y double prime plus 2y prime plus 2y equals 8 times e to the 2x. As discussed, the general solution is y equals y(h) plus yap. We'll start by finding the homogeneous solution, y(h). For y(h), we set the right side of the equation to 0. Y double prime plus 2y prime plus 2y equals 0. To solve this, we form the characteristic equation. The characteristic equation is m squared plus 2m plus 2 equals 0. We can try to factor this, but it doesn't appear to work. So we'll use the quadratic formula. The quadratic formula gives us m equals negative 2, plus or minus the square root of 4 minus 8 all over 2. This simplifies to negative 2 plus or minus the square root of negative 4 over 2. The square root of negative 4 is 2 times I, so our roots are 1 plus or minus I. These are complex conjugate roots. Whenever you have complex roots of the form alpha plus or minus beta I, the homogeneous solution is given by e to the alpha x times a constant c1 cosine beta x plus c2 sine beta x. In our case, alpha is 0.1 and beta is 1. So our homogeneous solution is y(h) equals e to the negative x times c1 cosine x plus c2 sine x. Now for step 2, finding the particular solution, yp. We find yp by looking at the form of the non-homogeneous part, qx. In this case, qx is 8e to the 2x. Our general rule is that if qx is a polynomial times e to the rx, the trial solution for yep is a times e to the rx. For our problem, r is 2. The homogeneous solution does not contain any e to the 2x terms, so we don't need to adjust. Our trial solution is y pct equals a times e to the 2x. To find a, we substitute this back into the original equation. The first and second derivatives of yp are 2ae to the 2x and 4ae to the 2x, respectively. Substituting these into y double prime plus 2y prime plus 2y equals 8e to the 2x gives us 4a to the 2x plus 2 times 2ae to the 2x plus 2 times a to the 2x equals 8e to the 2x. Combining the terms on the left, we get 10ae to the 2x equals 8e to the 2x. Dividing by e to the 2x and solving for a, we find that a equals 810, or 4,5. Therefore, our particular solution is y-IEP equals 4,5 times e to the 2x. The final step is to write the general solution by adding yh and yp. Our general solution is y equals e to the negative x times c1 cosine x plus c2 sine x plus 4 to 5 times e to the 2x. Remember this structure, yh plus yp. It's the foundation for solving all non-homogeneous linear differential equations. Let's move on to the next equation in this section, 2.2. The problem is v double prime minus 2y prime minus 8i equals 3 times e to the negative 2x. We'll follow the same two-step process. First, find the homogeneous solution yh, and then the particular solution yc. To find yh, we set the right side to 0. This leads to the characteristic equation m squared minus 2m minus 8 equals 0. This quadratic equation is factorable. It factors into the quantity m minus 4 times the quantity m plus 2 equals 0. The roots are m1 equals 4 and m2 equals 2. These are real, distinct roots. When you have two real, distinct roots, the homogeneous solution is of the form IH equals c1 times e to the m1x plus c2 times e to the m2x. So, for our equation, the homogeneous solution is y equals c1e to the 4x plus c2e to the negative 2x. Now for the second step, find the particular solution, yp. Our qx is 3 times e to the negative 2. A standard trial solution would be y equals a to the negative 2x. However, take a close look at our homogeneous solution. We have a c2e to the negative 2x term. Our trial solution is identical to a part of the homogeneous solution. This situation, where the trial solution is the same as a part of yh, is called a resonance or duplication. The solution won't work. We need to modify our trial solution by multiplying it by the independent variable, x. So, our new correct trial solution is ypp equals a times x times e to the negative 2x. This is a critical step that students often forget. Always compare your trial yp to yh. Now we differentiate and substitute back into the original equation. Using the product rule, the first derivative is a times e to the negative 2x minus 2x to the negative 2x. The second derivative is negative 4ae to the negative 2x plus 4ax to the negative 2x. Substituting these into y, double prime minus 2y prime minus 8y equals 3e to the negative 2x, we get a long expression on the left. Let's simplify. A powerful strategy is to group all terms with xe to the posh 2x and all terms with just e to the 2x. The terms with xe to the negative 2x are 4a plus 4a minus 8a. These add up to 0. This always happens when you've correctly identified the duplication. The terms with just e to the negative 2x are 4a minus 2a, which is 6a. So we have 6a e to the negative 2x equals 3e to the negative 2x. This tells us 6a equals 3. Therefore, our particular solution is yp equals 1/3 times x times e to the negative 2x. Finally, we combine the homogeneous and particular solutions. The general solution is y equals c1e to the 4x plus c2e to the negative 2x minus 1/2 bxe to the negative 2x. Question 2.3 changes the form of the non-homogeneous term. The equation is y double prime minus y prime minus 6e equals x. As always, we start with the homogeneous part. The characteristic equation is m squared minus m minus 6 equals 0. This factors to m such 3 m plus 2 equals 0, giving us roots m1 equals 3 and m2 equals 2. These are real and distinct. The homogeneous solution is therefore yeh equals c1e to the 3x plus c2e to the negative 2x. Now for the particular solution yp. Our non-homogeneous term qx is x. This is a polynomial of degree 1. For a polynomial term of degree n, the trial solution for yap is a polynomial of the same degree. Since our qx is a linear polynomial degree 1, our trial solution will be a linear polynomial x plus b. Check for duplication. Our trial solution x plus b is not a multiple of e to the 3x or e to the kx, so we don't need to adjust it. Now we find the derivatives and substitute. The first derivative of yp is a, and the second derivative is 0. Substituting these into the original equation, 0 minus a minus 6 times x plus b equals x. Expanding the left side gives us 6x minus a minus 6b equals x. To find a and b, we can compare the coefficients of the powers of x on both sides of the equation. On the left side, the coefficient of x is 6a. On the right, it's 1, so 6a equals 1, which means a is 1/6. The constant term on the left is a minus 6b. On the right, there is no constant term, so it's 0. Plugging in our value for a, we get 1/6 minus 6b equals 0, which gives us b equals 1/36. With a and b found, our particular solution is yp equals 1/6x plus 1/36. Finally, we combine the two parts. The general solution is y equals c1 e to the 3x plus c2e to the negative 2x minus 1/6x plus 1/36. This problem shows the method of undetermined coefficients for polynomial non-homogeneous terms. Question 2.4 combines the techniques we've seen so far. The equation is 2y double prime minus y equals x squared. Let's start with the homogeneous solution, yh. The characteristic equation is 2n squared minus m minus 1 equals 0. We can factor this as 2 minus plus 1 times m minus 1 equals 0. The roots are m1 equals 1 and m2 equals 1/2. They are real and distinct. So the homogeneous solution is yih equals c1e to the x plus c2e to the negative 1/5. Now let's find the particular solution yp. Kx is x squared, a polynomial of degree 2. Our trial solution yp must be a general polynomial of degree 2, x squared plus bx plus c. It does not conflict with yh, so this trial solution is correct. Now we differentiate yp and substitute back. The derivatives are yp prime equals 2ax plus b and yp double prime equals 2a. Substituting into 2i double prime minus e prime minus e equals x squared, we get 2 times 2a minus 2ax plus b minus x squared plus bx plus c equals x squared. Distributing the negative signs, we have 4a minus 2ax minus b minus x squared minus bx minus c equals x squared. Now we group terms by power of x to compare coefficients. Let's first rearrange the left side in descending order of powers of x. We have negative x squared plus 2a minus bx plus 4a minus b minus c. This equals x squared plus 0x plus 0. Comparing x squared terms, a equals 1, so a equals 1. Comparing x terms, 2a minus b equals 0. Plugging in a equals 1, we get 2 minus b equals 0, so b equals 2. Comparing constant terms, 4a minus b minus c equals 0. Plugging in a and b, we get 4 minus 2 minus c equals 0, which means c equals 6. We have found our coefficients. The particular solution is yp equals x squared plus 2x minus 6. Finally, the general solution is y equals yh plus yp. So y equals c1e to the x plus c2e to the negative x2 minus x squared plus 2x minus 6. This is a common type of problem, combining exponential and polynomial terms. Question 2.5 is a special case, a homogeneous second-order equation without an x term. The equation is 1/2 the y double prime minus 2y prime plus 2 equals 0. Notice it has a constant term but no explicit y term. Be careful not to confuse this with a term like 2e. The form of this equation is I double prime plus by prime equals c, which is a second-order linear non-homogeneous equation. This means it requires y(h) and y(p). To make it simpler to handle, let's multiply by 2 to clear the fraction. This gives us y double prime minus 4y prime plus 4 equals 0. We can rewrite this in standard form as y double prime minus 4i prime equals 4. Now we find the homogeneous solution. The homogeneous equation is y double prime minus 4y prime equals 0. The characteristic equation is m squared minus 4m equals 0. Factoring gives m to 4 equals 0. The roots are m1 equals 0 and m2 equals 4. They are real and distinct. The homogeneous solution is y(h) equals c1 e to the 0x plus c2 e to the 4x. Since e to the 0x is just 1, yh simplifies to c1 plus c2e to the 4x. Next, let's find the particular solution. Our non-homogeneous term qx is 4, which is a constant. We can think of it as a polynomial of degree 0. Our first instinct for a trial solution might be a constant, say, yp equals a. However, we must check for duplication with our homogeneous solution. Notice that yh contains the constant term c1. This is a duplication. Therefore, we must modify our trial solution by multiplying by x. The correct trial solution is yp equals a times x. Now we find the derivatives of this new trial solution and substitute. The first derivative of yp is a, and the second derivative is 0. Plugging these into our standard form equation, y double prime minus 4y prime equals 4, we get 0 minus 4 times a equals 4. This simplifies to 4a equals 4, which means a equals 1. So our particular solution is yp equals x. Finally, we combine yh and yp to get the general solution. The general solution is y equals c1 plus c2e to the 4x plus x. It's important to be vigilant for these special cases where duplication occurs with a constant term. We've reached the third section of our assessment. Here, the goal is to find a particular solution for each equation. The process is similar to finding a general solution, but with one crucial extra step. After finding the general solution, y equals yh plus yp, we will use the given initial conditions to solve for the constants c1 and c2. Let's begin with problem 3.1. The equation is dx plus y equals x plus 3te to the negative x, and the initial condition is that the curve passes through the point a0, 1. This is a first-order linear differential equation. We'll use the integrating factor method. The equation is already in standard form, dx plus pxy equals qx. So px is 1 and qx is x plus 3e to the negative x. The integrating factor I is e to the integral of 1 dx, which is e to the x. Now we can write the general solution formula. I times y equals the integral of I times q x. Y times e to the x equals the integral of e to the x times x plus 3e to the negative x dx. Let's simplify the integral. E to the x times e to the negative x is e to the 0, which is just 1. So the integral becomes the integral of x plus 3 dx. This is a very easy integral to solve. The integral is 1/2 g squared plus 3x. Don't forget the constant of integration, c. This is our general solution. Now for the new part. Finding the particular solution using the initial condition. The initial condition, 0, 1, means that when x equals 0, y must equal 1. We plug these values into our general solution. 1 times e to the 0 equals 1/2 times 0 squared plus 3 times 0 plus c. This simplifies to 1 equals c. So our constant is 1. Now we substitute c equals 1 back into our general solution. This gives us e to the x times y equals 1/2 v sub x squared plus 3x plus 1. To get the final particular solution, we solve for I by dividing by e to the x. Our particular solution is y equals 1,000 squared plus 3x plus 1 divided by e to the x. This solution is unique. It's the specific curve that passes through the point 0, 1. Question 3.2 is a first-order equation, but its structure suggests a different solution method. The equation is 3 plus 2x dx equals x ds, and the initial condition is x equals 1, y equals 1. Notice the terms involving both x and y. A good strategy is to rearrange it into the form di dx. Dividing both sides by x dx, we get di x equals d3 plus 2x over x. We can separate this into di dx equals 3yx plus 2. This equation has a special form. The right-hand side, fxy, can be written as a function of the ratio y power to x. This indicates that it is a homogeneous differential equation. Homogeneous equations are solved with a specific substitution. Let's let v equal y autos x. This means y equals vx. We then need an expression for di by dx. Using the product rule, di dx equals v plus x dvx. Now we can substitute both this and y extra vx into our rearranged equation. Replacing di dx and y, we get v plus x dv dx equals 3v plus 2. Now we have a differential equation in v and x. The beauty of the substitution is that homogeneous equations always become separable after this step. Subtracting v from both sides, we get x dvx equals 2v plus 2, or 2 times v plus 1. Now we separate the variables. Bringing all the v terms to the left and x terms to the right, we get dv over v plus 1 equals 2 over x dx. Now we can integrate both sides. The integral of 1 v plus 1 is ln vp, and the integral of 2 by x is 2 ln x. We add the constant of integration, c. To find c for our particular solution, we substitute back the initial condition. A common mistake here is to solve for v or y first. It's often easier to find c at this point. When x equals 1 and y equals 1, v is yx, which is 1, 1, L1. Substituting x to 1 and v1, we get ln minus 1 equals 2 ln 1 plus c. Since ln 2 equals c, we find that c equals ln 2. Now we can write our particular solution in terms of v. We have ln plus 1 equals 2 ln x plus ln 2. Using logarithm rules, we can combine the terms on the right. 2 ln x is ln by x squared, and adding ln 2 gives ln 2x squared. So ln v plus 1 equals ln 2 squared. Since the logarithms are equal, their arguments must be equal. The final step is to substitute v equals yx back and solve for y. We have yx plus 1 equals 2x squared. Multiplying by x gives y plus x equals 2x cubed. Therefore, our particular solution is y equals 2x cubed minus x. To check our work, we can plug the initial condition 1, 1 into this solution. Y equals 2, 1, or 3, 1 equals 2, 1 equals 1. It works. Question 3.3 is another first-order linear differential equation with an initial condition. The equation is di/dx plus y over x ln x equals ln x, and the initial condition is x equals 1 and y equals 1. The equation is already in standard form, di/x plus pxy equals y. Px is 1 over x ln x and qx is ln x. Now we find the integrating factor, I. I equals e to the power of the integral of 1 over x ln x dx. This is a very similar integral to one we saw in question 1.4. Using the substitution u equals ln x, we find that the integral is ln de ln x mar. Therefore, our integrating factor is e to the power of ln x, which simplifies to just ln x. This problem reinforces the pattern recognition we talked about. The general solution formula is y times I equals the integral of I times qx dx. Substituting our terms, we get y times ln x equals the integral of ln x times ln x dx, or the integral of ln x squared dx. This integral, the integral of ln x bar squared, requires integration by parts twice. For the first step, let u be ln x squared and dv be dx. After one step of integration by parts, the problem simplifies to x ln x squared minus 2 times the integral of ln x dx. The integral of ln x is a standard result, x ln x minus x. Substituting this, we get the final result for the integral, x ln x squared minus 2x ln x plus 2x. So our general solution is y ln x equals this expression plus c. This gives us the general solution for the problem. Now we'll use the initial condition to find c. The initial condition is x equals 1 and y equals 1. Let's plug these values into our general solution. Remember that ln 1 is 0, so every term with ln x will become 0. The left side is 1 times 0, which is 0. On the right, the first two terms are 0, and the third is 2. So 0 equals 0 minus 0 plus 2 plus c. This means c equals 2. Finally, we substitute c back into our general solution and solve for y to get the particular solution. Y equals x ln x squared minus 2x ln x plus 2x minus 2, all divided by ln x. This looks complex, but we arrived at it by carefully following the method. Question 3.4 is a first-order equation that requires a bit of clever rearrangement, as the hint suggests. We have dx equals 3 over the quantity 3x plus 2y. The hint tells us to write it in terms of dx dy. The initial condition is y equals 0 when x equals 1. The reason for the hint is that if we try to solve for y, we get a non-linear equation that's difficult to handle. But if we solve for x, the equation becomes linear. The derivative dx/di is the reciprocal of di, so dx di equals 3x plus 2y over 3, which can be written as x plus 2 to 3y. Rearranging this, we get dx/di minus x equals 2 to 3y. Now notice this looks exactly like our standard form for a linear equation, but with x as the dependent variable and y as the independent variable. The role of x and y have swapped. This is a brilliant trick. So we'll solve for x as a function of y using the integrating factor method. Pi is now the coefficient of x, which is 1. Q pi is the right side, 2 3y. The integrating factor I is e to the integral of py d, which is e to the integral of 1d, or e to the negative y. The general solution formula is x times I equals the integral of I times q, y di. Substituting, we get x e to the negative y equals the integral of e to the negative y times 2 3d di. The integral on the right requires integration by parts. We can pull out the 2/3 and focus on the integral of y e to the negative y di. Let u equals y, d equals e to the negative y di. Then do equals di, v equals negative e to the negative y. Using integration by parts, uv minus the integral of v d, we get e y e to the negative y plus the integral of e to the negative y d. This integrates to y e to the negative I minus e to the negative y. Multiplying by our 2 to the 3 factor, the full integral is 2 3e to the negative y minus 2 to the 3 to the negative y. So our general solution for x is x e to the negative y equals this integral plus c. Now we use the initial condition to find c. The initial condition is y equals 0 when x equals 1. Plugging these into our general solution, 1 times e to the 0 equals negative 2, 3 times 0 times e to the 0 minus 2 3d to the 0 plus c. This simplifies to 1 equals 0 minus 2 to the 3 plus c, so c equals 5 3. Substituting c back, we get x e to the negative y equals our expression plus 5 3. To find x, we multiply by e to the y. Our particular solution is x equals 2 3y minus 2 3 plus 5 3 to the y. This is a great example of being flexible and using the hint to change variables. Let's move on to problem 3.5, which is a second-order equation with two initial conditions. The equation is y double prime minus y prime minus 2e equals e to the negative 2x. We have two initial conditions, y equals 1 when x is 0, and x equals 1 when x is 0. Notice the second condition involves the derivative. As always, we find yk first. The homogeneous equation is y double prime minus y prime minus 2e equals EBO. The characteristic equation is m squared minus m minus 2 equals 0. This factors to m plus 2, m plus 1 equals 0. The roots are m1 equals 2 and m2 equals 1. They are real and distinct. The homogeneous solution is y equals c1e to the 2x plus c2e to the negative x. Now let's find yp. Our q at x is e to the negative 2x. A standard trial solution would be yp equals ae to the negative 2x. But before we proceed, we must check for duplication. Is e to the negative 2x part of our homogeneous solution? No, so our trial solution is valid. The derivatives are yp prime equals car 2ae to the negative 2x, and yp double prime equals 4ae to the negative 2x. Substituting these into the original equation, we get 4a minus 2a, all times e to the negative 2x, equals 1 times e to the negative 2x. This simplifies to 4a equals 1, so a equals 1/4. Our particular solution is y by share p equals 1/4 e to the negative 2al. Combining the parts, the general solution is y equals c1e to the 2x plus c2e to the negative x, plus 1/4 e to the negative 2x. Now we use the initial conditions. We have two constants, c1 and c2, so we need two equations to solve for them. This is why we have two initial conditions. Let's first use the condition y equals 1 when x equals 0. Plugging these into our general solution, we get 1 equals c1 plus c2 plus 1/4. This gives us our first equation. c1 plus c2 equals 3/4. For the second condition, we need the derivative of our general solution. Find y prime. E equals c1, e to the 2x plus c2 e to the negative x, plus 1/4 e to the negative 2x. Y prime equals 2c1, e to the 2x, minus c2, e to the negative x minus 1/2 e to the negative 2x. Now we plug in x equals 0 and y prime equals 1. This gives us 1 equals 2c1 minus c2 minus 1/2. Rearranging, we get our second equation. 2c1 minus c2 equals 3a2. We now have a system of two linear equations. We can solve by adding them together. The c2 terms cancel out. Adding the equations gives 3c1 equals 9/4, so c1 equals 3/4. Substituting this back into the first equation, we find that c2 equals 0. We have found our constants. c1 is 3/4 and c2 is 0. The particular solution is y equals 3/4 e to the 2x plus 1/4 e to the negative 2x. A key takeaway is that for a second-order equation, you'll need the initial value of the derivative as well. Question 3.6 introduces a differential equation where the variables are x and te, rather than the more common y and x. The equation is d squared dt squared plus 9x equals 9e to the 3t. We need to find the particular solution given x equals 1 and dx dt equals 3, 2 when t equals 0. The methods are the same, we just need to keep track of the variables. We'll find a homogeneous solution x as h and a particular solution x as p, where x is a function of t. The characteristic equation for the homogeneous part is m squared plus 9 equals 0. Solving for m, we get m equals plus or minus the square root of negative 9, which is plus or minus 3i. These are complex conjugate roots with alpha equals 0 and beta equals 3. The homogeneous solution is x equals e to the 0t times the quantity c1 cosine 3t plus c2 sine 3t. Since e to the 0t is 1, x as h is c1 cosine 3t plus c2 sine 3t. Now for the particular solution, xp. The non-homogeneous term is 9e to the 3t. Our trial solution will be x as ep equals ae to the 3t. We check for duplication. Are there any e to the 3 terms in our homogeneous solution? No. So this trial solution is valid. The first derivative of xp is 3ae to the 3t, and the second derivative is 9ae to the 3t. Plugging these into the original equation, we get 9ae to the 3t plus 9 times ae to the 3t equals 9e to the 3t. This simplifies to 18a, e to the 3t equals 9e to the 3t, which gives us a equals 1/2. So our particular solution is x sub p equals 1/2 e to the 3t. The general solution is x equals xh plus x sub p. X equals c1 cosine 3t plus c2 sin 3t plus 1/2 e to the 3t. Now we use the initial conditions to find c1 and c2. The first condition is x equals 1 when t equals 0. Plugging this into our general solution, we get 1 equals c1 cosine 0 plus c2 sine 0 plus 1/2 fp to the 0. This simplifies to 1 equals c1 plus 1/2. So c1 equals 1/2. For the second condition, we need the derivative of our general solution with respect to t. Now plug in t equals 0 and x prime equals 3/2. We get 3/2 equals 0 plus 3c2 plus 3i2. This means 3c2 equals 0, so c2 equals 0. With our constants found, c1 equals 1/2 and c2 equals 0, we can write the particular solution. X equals 1/2 cosine 3t plus 1/2 e to the 3t. This problem serves as a good reminder that the underlying principles remain the same even when the variables change. Question 3.7 is a second-order linear homogeneous differential equation with constant coefficients and initial conditions. The equation is bat times the second derivative of s with respect to t minus ds to dt minus 2s equals 0. The initial conditions are s equals 1 when t equals 0 and ds dt equals 2 when t equals 0. This is a homogeneous equation, so we don't need a particular solution xp. We only need to find the general solution, x or h, and then use the initial conditions. The characteristic equation is 3m squared minus m minus 2 equals 0. We can solve this by factoring. It factors into 3m plus 2 times m minus 1 equals 0. The roots are m1 equals 1 and m2 equals 2, 3. These are real and distinct roots, so the general solution for s is c1e to the t plus c2e to the negative 2, 3t. Remember, for a homogeneous equation, the general solution is just the homogeneous part. Now we use the initial conditions to find c1 and c2. The first condition is s equals 1 when t equals 0. Plugging this into our general solution, we get 1 equals c1 plus c2. This is our first equation. For the second condition, we need the derivative of our solution with respect to t. Now plug in t equals 0 and s prime equals 2. We get 2 equals c1 minus 2, 3c2. This is our second equation. We have a system of two linear equations. Let's solve for c1 and c2. We can subtract the second equation from the first. c1 minus c1 is 0. c2 minus negative 2, 3c2 is 5, 3c2, and 1 minus 2 is 1. So, 5, 3c2 equals 1, which means c2 equals 3, 5. Substituting c2 back into the first equation, c1 plus 3, 5 equals 1, which gives c1 equals 8, 5. With c1 equals 8 to 5, and c2 equals 3f5, we can write the particular solution. S of t equals 8 to 5, e to the t minus 3f5, e to the negative 2, 3. This problem reminds us that even for homogeneous equations, initial conditions are needed to find the specific solution. We've reached the final question of our assessment, question 4. This is a word problem. It states that the gradient of a curve at any point, xy, is 2y minus x. We need to determine the equation of the curve if it passes through the point, 0, 1. The first step in any word problem is to translate the words into mathematical symbols. The gradient of a curve is the same as the derivative of y with respect to x, which is di x. So the statement, the gradient is 2e t x, translates to the differential equation di dx equals 2y minus x. Rearranging this into standard linear form gives us di/dx minus 2y equals negative x. This is a first-order linear differential equation, so we will use the integrating factor method. Px is 2 and qx is x. The integrating factor I is e to the integral of 2 dx, which is e to the negative 2x. The general solution formula is y times I equals the integral of I times q cx d. The integral of xe to the negative 2x dx requires integration by parts. Let u equal x and dv equal e to the negative 2x dx. The integral evaluates to negative 1/4 by e to the negative 2x minus 1/4 e to the negative 2x. Plugging this back into our general solution, and remembering the negative sign out front, we get ye to the negative 2x equals 1/2 e to the negative 2x plus 1/4 e to the negative 2x plus our constant c. Now we use the initial condition to find the specific value of c. The curve passes through the point à 0, 1, so we plug in x equals 0 and y equals 1. This gives us 1 times e to the 0 equals u plus 1/4 e to the 0 plus c. Simplifying, we get 1 equals 1/4 plus c, so c equals 3/4. Substituting c equals 3/4 back into our general solution gives us the equation of the curve. ye to the negative 2x equals 1/2 of I guys e to the negative 2x plus 1/4 e to the negative 2x plus 3/4. We can simplify this by multiplying the entire equation by e to the 2x to solve for y. This gives our final answer. The equation of the curve is e equals 1/2 p t cents plus 1/4 plus 3/4 e to the 2x. This is a perfect example of applying a differential equation method to solve a geometric problem. We have now worked through the entire summative assessment for Module 4. We've solved 17 different differential equations, covering a wide range of types and methods. Let's recap the key concepts you've mastered today. We've learned to recognize and solve first-order linear differential equations using integrating factors, a powerful technique that turns a non-exact differential equation into an exact one. We've also seen how a simple substitution can transform a nonlinear or homogeneous equation into a solvable linear one. For second-order equations, you now know how to find the characteristic equation to solve the homogeneous part, and how to use the method of undetermined coefficients to find the particular solution. Remember the importance of checking for duplication. It's a common trap, and failing to adjust your trial solution will lead to an incorrect answer. And finally, for particular solutions, you've seen how initial conditions are the key to finding the specific curve that satisfies a differential equation. Thank you for watching and learning with Earthly Teachings. I hope this detailed tutorial has made solving differential equations much clearer. Your understanding is your superpower in mathematics. Continue practicing these problems, as mastery comes with effort. If you found this video helpful, please like it, subscribe to the channel for more clear and powerful mathematics lessons, and share it with your fellow students. See you in the next video.